Swayam Prabha. Digital India. Educated India.
You cannot take it same as R. So, it will be P by T minus 1 exactly. Good. Yeah. So, this number I am going to write this as R has P choices, S is other than R with the same mod. So, it will be I am going to say floor of P by T minus 1. Okay. So, this is P into less than or equal to floor of P by T. I am going to say P plus T minus 1 by T. It's rounding up. We are rounding up because P may not be a multiple of T and so on. When I round it up, I may add at most T minus 1, and there is minus 1, and this is equal to this one and that one. I am going to cancel it. And lo and behold, this is exactly what we wanted to show. What did we want to show? That number of these functions is cardinality of f by t. What is cardinality of f? That is p into p minus 1. Did I show that? Yes. Okay. Good. Questions? So, is that clear? So, the key thing which we really used is that in the mod P world, R and S are different. That is all. And this is because P is chosen as a field. P is a prime number. So, in this A, B, all it is doing is somehow putting things in some sort of an order. So, if A, B is random, then you just think of it as you are doing a random permutation of your elements, and then you are doing mod T. Okay, so this is probability that this H A B of x, where A and B are chosen at random, is equal to H A B of y is at most 1 over t. This is 1 over t fraction of the total number of functions, which is p into p minus 1. Okay, so this is very powerful construction. I mean, very simple but powerful. It simply says that this small sized family somehow behaves like all functions from u to t. So, if I want to randomly pick a function, you do not have to pick from this all function, pick from this function, at least from the point of view of achieving this 2 universality, you have this. Okay, now let me give you a acute application of this. And then we will extend to K universal. Okay, I will just K universal I may not prove or do anything, I will just say what the function is and we are done with it. But here is a nice application, and that is, you already saw yesterday this problem of max cut, right? No, max cut also in the tutorials, right? Oh, you use the term min cut. Okay, let me define it and do it. Okay. So, min cut is also interesting, max cut is also interesting, but they have contrasting algorithmic behavior. So, I will tell you more about both. So, let us talk about cut. Right. So, your input is a graph, undirected graph with vertex set and edge set. And what is the goal? Find a partition of the vertex set such that, so S is contained in V, T is contained in V, S and T are disjoint, and S union T is equal to V. So, I just want a partition of the vertex set such that the number of edges across the cut, right, the size of this set U comma V, U in S, V in T, this cardinality, well, is maximized. This is max cut. You can also talk about minimized. This is min cut, right. One of these problems is polynomial time solvable. Which one? Have you seen this? Okay, you may or may not have seen. So, min cut can be solved using max flow. Anybody has seen max flow min cut theorem? Okay. Menger's theorem is a variation of it, yeah. So, but you have seen flows, max flow. Anybody else who has seen max flow? Okay. So, you can talk about, you know, an ST cut where networks in algorithm, in the advanced algorithms, typically initial course and algorithms may or may not cover it, but the second course and algorithms should cover max flow, min cut, or even in graph theory course, right? Graph theory course should cover that. So, you can talk about an ST cut where S is a small specific vertex in the graph, T is a small specific vertex in the graph, and now you can talk about separating S and T, or the partition where small s in capital S and small t in capital T such that minimum number of edges go across. Now, this can be solved using powerful application of max flow. Okay, max flow can be solved in polynomial time. This is one of the beautiful algorithmic or graph theoretic questions using which you can solve this in polynomial time. So, when I say this is solvable in poly time, I mean the ST cut problem is solvable using max flow, but then you try all possible small s and small t and you can solve min cut in polynomial time. There are other ways to do it as well. Max cut, on the other hand, is NP complete. Again, I think I already asked this. How many people have seen NP completeness? I'm not going to ask about it. Huh? You have a general knowledge on NP complete. I'll ask you about it in the break. How many others have heard of? Okay, good. So, at least you have heard of NP completeness. So, it's believed that NP complete problems cannot be solved in polynomial time. This is one of the famous open problems in computer science. We don't know yet, but it's widely believed that you may not have an efficient algorithm for an NP complete problem. So, in particular, if I want to find the partition which maximizes the number of edges across, that is a hard problem. So, what we are going to do is to come up with some sort of an approximation algorithm for it. Okay. So, that means I may not be able to find that partition that maximizes the number of edges across, but give me some partition which gives you a lot of edges across, okay, and that lot has to be quantified appropriately. Okay. And so, yesterday you saw a randomized algorithm, right, Woodluck? You saw a randomized algorithm which does something, which gives you a partition where anybody wants to complete, we followed. So, what we showed is that there exists a partition of the vertex set such that at least so many edges are across the cut, m by 2, half the edges on expectation. There is a randomized algorithm. I will repeat it again, that there is a randomized algorithm. So, okay, so approximation for max cut. So, first what we will show, so finding the optimum is hard. So, I want something close to optimum, right. So, I want a algorithm which is fast, polynomial time. It should give you a cut that is not very bad compared to the optimum, but I do not even know optimum is. So, how do I know how bad it is to the optimum? We will compare it with some sort of a bound for the optimum, okay, and say if the optimum cut value is 200, I will produce you something which is at least 100, okay. So, it's I am never more than, not worse than half of the optimum, okay. So, that is the goal. So, the first claim is there exists a cut with at least m over 2 edges, okay. And how did we show this? We have seen this yesterday. So, what is the partition? I have to partition the vertex set into 2 such that at least half the edges go across, okay. So, what partition should I do? Yeah. No, my goal is to come up with S and T, right, this S and T. So, give me an S and give me a T, and then we will try and argue that, oh, how many edges are going across this. And of course, first thing you should ask is give me the graph, right. But I am going to say for any graph, there is a generic way of getting S and T. We are doing randomized algorithms. So, what? Sorry? Yeah. So, what does randomly mark mean? So, what do I do? More precisely, yeah, that is the idea. For every vertex, I need to figure out whether it should go to S or T. How do I figure out? Yeah, but just tell me a little more precisely what do I do to figure out whether I should put it in S or T? Yes, random is correct, but when you want to really implement it, what do you do? Toss a coin, right? Or consult a random number generator to give me something 0 or 1 or something between 0 and 1. If it gives me less than half, I will put it in S. If it's greater than or equal to half, something, right? Basically toss a coin. If it comes head, put it in S. If it comes tail, I will put it in T, right? So, that is my random partition. So, the partition is clear. Right now, we are going to talk about randomization, randomized algorithm, randomized partition. So, the partition is, so uniformly at random, put x in S or T where x is a vertex in the graph. So, for every vertex, I will toss a coin. If it comes head, I will put it. Let us assume I have a fair coin, and based on this random toss, I will put it in S or T. Okay. Now, let us see how many edges. So, I have gotten my S and I have gotten my T, randomly partitioned. Now, I want to understand how many edges are going across. That will be a random variable, because this partition is random. So, I can only talk about the expected number of edges going across the cut, right. My interest is an edge like this. So, given u v in H, what is the probability that u v is in the cut? I haven't defined really cut, but I hope you understand. This is equal to probability that when is u v in the cut? When u in S, v is in T, or u in T, v in S. What is the probability of this happening? 1 by 4. Okay. Why is it 1 by 4? Half into half plus half into. What am I assuming here? Why is it half and half? So u in S, v in T is 1 over 4. Sorry, so it's half, right? Yeah, why is it 1 over 4? Let's be very careful. U in S, v in T. I am assuming that these coin tosses are independent. But if you look carefully, I don't need full independent. All I care about is this pairwise independence. That if you pick any pair of, this is the two universal thing. If you pick a pair of vertices, their coin tosses are independent. So, u in S, v in T has a probability of 1 over 4. Similarly, the other probability is 1 over 4, and I use union bound, and I get 1 over 2 as the probability that this edge is across the cut. Okay. The key thing to note is that I am using pairwise independence. Okay, I should have talked about this in the hash family thing. I'll come back to it later again. Okay. So, now expected number of edges in the cut. What is this? Why? Summation u v in E, expected or probability that u v is in the cut. Which we argued it to be half. So, if there are m edges in the graph, then the expected number of edges is m over 2. Okay, and the key thing to note is that for the analysis to go through, all I needed was this coin tosses are pairwise independent, because it is this step, probability u in S, v in T, where we are measuring what is the probability. This is the product of these two probabilities, half into half. All I needed was this pairwise coin tosses to be independent. Okay, now I claim that I have proved the claim. Is that true? What I wanted to show is that there exists a partition which has at least m over 2 edges. But what I really showed is that I did a random experiment, and I said in this random experiment the expected number of edges across is exactly m by 2. Does the claim follow from that? Can somebody give me an argument why? So, I say hence there exists ST such that number of edges in the cut ST is greater than or equal to m over 2. Okay, and you've probably seen this probabilistic method in the tutorials. So, it is very useful observation, but not very hard to argue. All I am saying is, hey, if the average mark is 45, there must be somebody who got greater than or equal to 45. How can the average be 45. If everybody got less than 45, the average will be less than 45. So, if the expectation is average. What is the expectation over all? Really, if you think about it, the expectation is over all possible partitions here. So, if the average over all possible ST partition is m over 2, there must be one partition where the number of edges is at least m over 2, because if everybody is less, the average cannot be. That is all. So, there exists a cut where the number of edges across the cut is at least m over 2. Okay. So, now our goal is to find such a cut, okay, and I am going to give that as the solution of my approximation algorithm, right. My goal, remember, is to design an approximation algorithm for max cut, which is at least, not too far from the optimum, right. So, maximum can be m, all, maybe the whole thing is a bipartite graph, all edges are across, there is a partition where every edge is across. So, m is a maximum, but I will find a really, I will find a cut which exists in any graph by this claim. I will find such a cut in polynomial time and say that is my cut and that is my approximation algorithm, which produces you at least half optimum, right. That is my goal. So, the goal is to find such a cut deterministically in polynomial time. If you want a randomized algorithm, here it is. I know, just do a randomized experiment, but I claim that you can actually find a deterministic algorithm using two universal hash family, which we came up with, right. So, where is the randomness here? And I want to get rid of the randomness. Where was the randomness in this partitioning? Coin toss, right, to say whether I should put it in S or T. Instead of coin toss, I am going to use my universal hash family and get the coin tosses, whether it is a head or tail. I am going to use my universal hash family, which will give me this coin tosses. I will use that and then argue what I need. Okay. So, de-randomizing the algorithm, the above algorithm. Okay. So, now I am going to use this family HAB. Okay, I should have indexed from U to T as I defined before, but now my universe is the graph's vertex set and my table is going to be 0 1. Okay. So, what am I doing? So, what is this function doing? This function takes the vertex set V and assigns some of them value 0 and some of them value 1, okay, which defines a partition. Okay. So, take this two universal hash family, right. I have choice of u, t, I mean that family is very general, defined for any u and any t. So, let me define it for my vertex set and 0 1 is my range. So, it gives me a partition. Let us understand the two universal property. So, what is the two universal property I know is that for all vertices u v, where u is not equal to v, probability that, what did I call, HAB, u is equal to HAB of v is at most what? That is the number of functions. But in terms of probability, 1 by t, what is t? 2 for us. So, it is at most half. Okay. So, this is pairwise. So now, this is that's all. I've given you an algorithm. What is my algorithm? Take a 2 universal hash family here. Let's call this. I've been calling everything F. Let's stick to it. It just assigns every element a 0 or 1. So that's my coin toss outcome. Okay, so that gives me a partition. And the property of this partition is this: if you pick a pair of vertices, the probability they get mapped by any function here is at most half. Okay, good. So now let's do our analysis. So how many edges are there? So this at this moment it looks still like a randomized algorithm. It is a randomized algorithm because H is random. It is a randomized algorithm. So now let's look at expected number of edges in the cut. Okay, so I hope it's clear. So what I am saying is I pick a 2 universal hash family where the range is 0, 1. That defines where the domain is my vertex set. That defines a partition of the vertex set into 2 sets. That gives me a partition. Now I look at the cut across and look at the expected value of the cut, where the expectation is over all the functions in this family, right? Because H is a random function. Now it's the same argument. If you pick any edge, what is the probability? So, yeah, I want to compute this. Let's say UV is an edge. What is the probability that UV is in the cut? Yeah, can somebody tell me? Probability is UV is in the cut is the probability that U and V get different values in the partition, in my coloring, in my coin toss, whatever. If U and V get different values, U goes here, V goes here, or V goes here and U goes here. They should get different values, then it will be in the cut. What is the probability that they will get different values? Why? Is at most half. So, the probability that they will get different, because we know that the probability that they will get the same value is that they will get into either both in S or both in T as a probability of at most half. So, they will be split is the probability at least half, right, 1 minus this. So, that is greater than or equal to half. So, now expected number of edges in the cut is greater than or equal to M over 2. Okay. This is not yet de-randomization. It's still randomized algorithm because I picked a random hash function from this family. But the nice thing about this family is that this family size is small. What is the size of this family? What was the size of the family? Let's go back here. No 2 power. Where what is the size of our universal hash family? We defined, right? This was the size of the family. P into P minus 1. Just P into P minus 1. Mod? Number of vertices, sorry, mod V into mod V minus 1. Well, this may be little more because I have to, P may be larger than V. P is a prime. Now, size of V may not be a prime, but it may be like 2 times V. Whatever it is, it's order n square. Okay. The number, because that was a big thing, we made a thing, right. The total number of functions in all functions is huge, P power T or T power P, whatever, I forget. But this small family has a similar behavior in terms of collisions, and the size is only P square. right, where P is the domain size, order of the domain size, and for us it is just the vertex set. So, it is order n square. So, I am going to say order V square, which is like n squares, number of functions are there. So, now let me see. So, what have you shown is that take this family of some n square functions and pick a random function from here and give your two coloring, the partition, and expected size of the cut is already as good as you want, at least m square, or at least m by 2. Okay. Expectation now is on this small sized family, right, which means that there is some function in this family which will give you a cut of size at least m by 2. I can do brute force and compute it, right. So, this implies there exists a function f in this family f, and if we use f to partition V to get S and T, the cut value of S and T is at least m over 2, right, because earlier I said this claim there exists a cut, that partitioning was with over all random functions, right, the all functions, that is too many and I do not want to do it, but quickly what we realized that pairwise independence is what we really care about in the analysis, and so a 2 universal hash family can give you pairwise independent bits, use that to do your partitioning, and then in that family the expected size, if you use a random function to do your coloring, is at least m over 2, and so now you can de-randomize it. How do I de-randomize it? So, find it by brute force, try one by one, right. So, try all order n square functions in F and pick the partition that gives the largest, to get a cut of size at least m by 2. Okay, any questions? I will just take 5 more minutes to. So what, just to summarize what we did, we defined this 2 universal family of hash functions, and the collection of all functions is 2 universal, but that is too much, too many functions, too much space to store it, and I argued that there is a very simpler, using some little bit of number theory, there is a small size family of 2 universal hash functions, which is easy to store, easy to compute and all that. We are going to see a lot of applications of this later on in this big data world, especially when I want to represent element not by an element, but by its image of a function. But here is a very nice application to de-randomize an randomized approximation algorithm. I will just spend 2 minutes or 5 minutes to just say what is K universal and and say that there is a K universal hash family, can also be defined very similarly, and that is also useful. Okay, so maybe I should. Yeah, so K universal family. So, again you have a family F of functions from U to T, I didn't define 2 universal this way, but this is also another way to do it. Maybe that's for tutorial, which is that for all x1, x2, some xk in U, all distinct, and y1, y2, yk in T, probability that when I pick a random function, h of x1 equal to y1 and h of x2 equal to y2, is exactly equal to the product of the individual probabilities. Okay, I did not define 2 universal this way, but you could also define it this way. Maybe that's something for the tutorial to check, that an equivalent definition of 2 universal would be that if you pick any pair x, y and a, b, probability that x equal to a and y equal to b is equal to the product of the probabilities that x equal to a times probability x equal to. So, this is also equivalent to this k wise independence, like the pairwise independence, this is k wise independent, and again you can.
You should still say that each of this is 1 by t.
I think it follows. I may not need to say it, but yeah. So, that is the uniformity thing. And there exists. So, what we can do is this function h or a1, a2, ak for defined by a1 plus a2x plus a3x square plus ak x power k minus 1 mod p is k universal. Okay. So, maybe this can be looked at in detail in the tutorial if there is time. So, the key thing to argue this is this yeah. So, we argued that if x and y are different and a, b are from this field, then ax plus b and ay plus b are different, right. So, if or there is a so what we can do is if x1 gets mapped to y1 in this polynomial function and x2 gets mapped to y2, x3 gets mapped to y3 and so on, there is a unique h which will do this mapping. Okay, because you can do this inverse like exactly what I did. So, if R and S are fixed, then x and y are fixed, kind of argument you can show that. So, there is this van der Waals matrix you can write to solve this system of linear equations, invert it and you will get your original thing. So, for number of functions, number of a1, a2, ak which will map to y1, y2, yk is unique once you give x1, x2, xk, and that is because this system of linear equations has a unique solution. Okay. You may not have followed or I may not have said everything correctly. If there is time in the tutorial, you can deal with it. Otherwise, it's a reasonably straightforward generalization of 2-wise independence. So, the size, instead of p square, it will be like p power k or something. And that is useful whenever you are looking at k-wise independent family, of random variables, then you want to say that such a family generates you k-wise independent family of values. Yeah, random values. Okay.